Posso? Okay. So you see, this is very heavy. Some part of it is lecture. Okay. Okay. So we have Peter Tuthill in a, let's say, out of the normal stream seminar, just because we collaborate for breakthrough. So we're finding a planet around. Try finding a planet around Alpha Centauri or Sirius.
We'll find a planet.
Of course. Yeah. And I mean, Peter is from Australia, but he you graduated in Queensland because it's Qantas comes from Queensland and Australian territory. And then went to Cambridge, UK, then to Berkeley, California. And finally back in 2000 with the University of Sydney. And he will speak about imaging. He is an expert on high resolution imaging and interferometry for finding planets around nearby stars or something like that.
That's good.
Thank you.
Oh, thanks, Roberto. So I'd like to thank the Observatory of Padua. I've just been to a, is this sound quality okay for everyone? It sounds a little bit loud in my ears. I don't know if I can turn this down.
Yeah, you very well.
I'm okay. Yeah, I just been on the tour up the tower, and it's stunning up there. You astronomers are extremely lucky to have this wonderful institute in this historic area. And I learned two things from my tour. One is that your institute here is 3 years older than the discovery of my country, which was in 1770. I believe it was 1767. And the other thing I learned is that you keep your PhD students in a basement where 10,000 people died in their own blood. So I think this is possibly something we're not going to adopt in Sydney, but a very interesting building you have. So this is, of course, the nation that was found in 1770. I'm required by my university to put pictures of beaches up because, particularly in the northern winter, if there are any students watching, we have a lovely environment there, and we're very interested in building linkages with Italy, very interested in people coming, working with us. That's my university. So I do quite a lot of astrophysics, and I'm not going to talk about astrophysics here today. This is a recent result that was published on some funky imaging systems that we work on. So instead of talking about my astronomy, I'm going to talk mainly here about instrumentation. So I hope there are enough geeks in the audience to be interested in these kind of things, but we're specialists in the manipulation of light. In the, as many people are, of course, it's becoming more and more the norm in astronomy that advanced techniques to understand the light, to manipulate it, use photonics, are becoming the standard practice in advanced instrumentation. So let me, first of all, this talk's mainly about TOLIMAN. That's mainly what I'm here for. But I'm going to talk a little bit, first of all, just give you a little taster platter of the kind of things my group does in Sydney. It kind of all started here at Keck, and I had this fun experiment where I used to go out and mount an actual physical mask over this telescope. That's in the top left there. It was a sign of a sort of a trash can lid. And a lot of things have now sprung from that original experiment that we did sort of in the 1990s, the mid-1990s, the late 1990s. This technique seems very, very wasteful. You throw away most of the starlight. But in fact, what you do is you turn a large aperture into a sparse element array. You've wasted a lot of the starlight, but it turns out that the starlight that you do get through forms an interferogram, and you can calibrate that interferogram with much higher precision than you could have calibrated it had it just come. And we have these on the LBT. You'll see the Pupil up there. Every single 8-meter telescope now has one of these. Almost all of them are of my design. We're doing fun things now, trying to advance this technology. So this is just a slide of astrophysics. I'm not going to try and go into it. Well, it turns out when you image the universe at high spatial scales, it becomes a dynamic place. You can make movies of things. It's all cool. There are 8 Nature papers on this slide. There are a whole bunch of results. So we sort of done well with what started out as a dustbin lid with holes in it that cost me $50 to get made in the machine shop. So it's sort of, interferometry is really what powers our group, understanding the starlight from a very interferometric perspective and then bringing that to to your instrumentation. We've got an instrument on the Subaru telescope. It's lots and lots of mirrors and polarization switching apparatus, and also one of these masks. And with that apparatus, we're able to reveal the inner environments around. That's an image of the dust shell with the star removed. In fact, in polarized light, you only get polarized light from the scattering above the atmosphere. So we can make images of polarized light, and we can reveal this hidden world of faint structures in the immediate environment of bright stars. We are trying to address that problem I'm talking about of wasting the light by going more advanced with the photonics. So in the upper panel here, you see a new age or a new generation aperture mask. Rather than wasting all the light, it still does waste quite a lot of the light, but these panels aren't now holes in a mask, they're now holographic phase gratings. And so rather than throwing the light away, the circular holes are the old mask, and they give you a pattern in the core of in the bottom right here. But the light that lands in the hexagonal areas, we redirect to different areas on the array, and we can make non-redundant masks at will, essentially. You can just redirect the starlight wherever you like. This is an amazing technology. It's a thing called geometric phase. So if you talk to me afterwards about geometric phase, it's wonderful. It gives you this exquisite control over the light that's coming into your telescope. So we're trying to break these boundaries with these interferometric techniques. Another way we're proceeding to try and take all of the advantages of these interferometric modes and none of the disadvantages, none of the loss of light, is a thing called a Pupil Remap Err. So we take the light beam from the telescope and we pass it through a segmented mirror, and then we can inject it into this device in the middle, this block of glass. And that's basically this wonderful piece of plumbing. You can make these blocks using a laser, and you can sculpt a waveguide through the glass, and as you move the glass underneath the laser, you can, with an XYZ computer-controlled stage, you can sculpt a channel or a pipe for the light to go wherever you like. So this device is able to rechannel the starlight, and it's able to preserve coherence. So it's a coherent remapper. We can remap the pupil from the initial, what I would call a redundant geometry. So we can make a mask, essentially, using plumbing of the light through these optical fiber chips. And we've put these things on Sky, and you just have to design in 3D CAD packages where you want the light to go, and then you can just fabricate a chip that does this. Going another step further into this photonic domain, we can build beautiful little lenslet stacks on top of these chips so that you don't have to inject it. So this is a 3D printed, this is a micrograph. On the right-hand side here, you see the micrograph of these 3D printed lenslet stacks. So we can feed the light into these waveguide chips. And then what we ultimately do these is build nulling interferometers. So we take the starlight and we try and form a destructive null so that the bright starlight is all channeled down one arm of the interferometer, and the other arm of the interferometer has no photons in it, unless there are some photons that aren't nulled, and the photons that are not going to participate in the nulling are the ones that are a little tiny bit off axis. So this is a way to try and reveal a faint planet next to a bright star by nulling the star out. So these are technologies that people are all working on, and we're doing it with these photonic kind of ideas. Just finally, I wanted to throw in one more fun experiment we did. We used the Cassini spacecraft as an interferometer, or more accurately, we used the rings of Saturn as an interferometer. So if you, most people are familiar with lunar occultations, when a star passes behind the limb of the moon. In fact, Arthur Eddington, 100 years ago, proposed that you should be able to see a little fringe, a little ringing, as the star vanishes behind the limb of the moon. This is occultations. This has been used for a long time in astronomy to measure the sizes of stars. it turns out that as a star passes behind the ring plane of Cassini, from Cassini's perspective, the rings turn from being completely transparent, deep sky, into completely opaque, just a brick wall, over about 10 meters. So the ring plane is this amazing razor blade lying in the sky. It's a beautiful demonstration of this kind of physics. So as from the perspective of Cassini, watching a star pass behind the ring plane, there are all these different edges. And as the different edges cut through the star, you get different, it's basically like tomography. You get different slices in different orientations as that razor blade cuts across the star. And in fact, we were able to recover sizes, but also the little star up in the left, the red star, shows you the angular diversity you get as the star passes behind the ring plane from Cassini's perspective. And we were able to recover two-dimensional images of celestial targets with this. It's kind of a fun interferometric experiment. And just to show you that these experiments are alive and well, even though they do seem very primitive, it's just a plate where you waste the starlight. We've actually got one now flying aboard the James Webb Space Telescope. So this is cryovac 3 data. We've got an Aperture Mask aboard, which will launch in 2021 now. It's the latest launch date for that. So that's a preamble. That's the taster of all of the other things we do at Sydney. The thing I'm here to talk about really is a small space mission called TOLIMAN. And it has a funny origin, actually. It's got an interesting history. There's a billionaire called Yuri Milner who works, he's Russian origin, but he lives and works in California. And he's donating a lot of money into science through a thing called the Breakthrough Initiatives. And you've possibly heard of this one. It's the most famous of those initiatives, where he has the ambition to blast a very, very low mass object. He's holding this 1 gram chip in his hand. And he has the ambition to blast that to Alpha Centauri, or a nearby star which hosts a planet. And the brief that he's given to the scientist is that he wants to signal back before he dies. So the funder's lifetime is folded into the mission deliverable. It's got if he's going to live 40 years, then from now, then if you go at 10% the speed of light, you've used up your budget getting just to Alpha Centauri. So you need to go very, very fast in order to meet his requirement. So the requirement is something like 20% the speed of light, which is an insanely fast object. Mankind hasn't launched anything. For reference, the fastest space probes we have, Kuiper Belt Express, I think, would take about 100,000 years of order just to get to Alpha Centauri. So this is breaking the speed barrier. So this is a program called Breakthrough Starshot. Most people have at least heard of this once or twice. I can field questions about Starshot. But if you're going to spend $1 trillion building a technology that's going to get you to the nearest star system, you better have somewhere to go. You better have something interesting to get to at the far end. So that raises the question, is there a planet in the Alpha Centauri system if we spend all this money to go there? And in particular, we need, ideally what we'd like is we'd like an Earth analog. We'd like something small and rocky, and we'd like something in a temperate orbit. And we'd like all of these things because we don't understand whether life could potentially exist on a world very different from our own, but we know we've got one data point. We know life can exist on a world like our own. So it's basically a kind of an anthropic argument. So these are the kind of, we can now leave Starshot out there in its own little bubble of possibility. This is now a much more, I guess, more defined and more tractable present-day scientific question. Is there a planet around the Alpha Centauri system? And surprisingly, we have no idea. Alpha Centauri is in the lower left here. Northern Hemisphere people aren't probably very used to this vision of the night sky because it's quite far south. There's Alpha Centauri and Proxima Centauri, which has a known potentially temperate zone planet. It's a red dwarf, and it's actually quite a long way away on the sky. It's debated whether it's even a bound triple. But Alpha Centauri itself consists of A and B, which have the names Rigel, Centaurus, and TOLIMAN. the two stars that comprise that system. And the funny thing about this slide is that you're looking at all these stars and you think, yeah, they all look kind of the same. Well, no, they're not. Alpha Cen is approximately 100 times closer in your field of view than all of the other stars you're looking at there. They're all 1 kiloparsec away. So they're essentially 100 times further away and 10,000 times brighter. So you look at that star field and you think they're all kind of the same thing, but they're not at all. This thing is a very, very weird object. It's a very dim object, very, very close up compared to everything else in the frame. Having said that, we're still very lucky to have Alpha Cen there at all. It's a sun-like star, and if you run history forward or backward in time over tens of thousands of years on the lower right here, you'll find that Alpha Cen is only the closest object to us for a very limited window of history. Normally you'd expect one of these dim red objects, you know, Ross 248 or Galisa 445 to be the closest object to Earth. Alpha Cen's a binary, and it's not quite equal binary to a 2 or 3 to 1 flux ratio. And it's got these unusual properties. It's this sun-like star really near to the Earth. So the habitable zones, it turns out, are stable. You can see that on the lower panel here. The habitable zones lie interior to the binary stability. So we do have the hope that there could or should be planets that are in those zones, particularly small rocky ones. So the funders' question really is, how do we go about finding them? So the most productive way to go finding planets is, of course, transits, things like Kepler mission. Wait till something passes across the line of sight, the star blinks, and you know there's a planet there. Of course, that works when you've got catalogues of tens of thousands of stars to choose from, and you get lucky with 1% or much less than 1% of them. So that's not going to work when you ask the question, is there a planet around an individual star? The other way that planets are found is Doppler radial velocity. The planet will tug the star, and the star's motion in the line of sight is registered in the spectrum. It turns out that for a habitable zone planet, those signals are extremely small. Doppler RV loses sensitivity and with orbital radius, and it's very, very hard to get down to 1 Earth mass. We'll see that in a second. So many scientists have kind of accepted the idea that if you want these very nearby objects, the easiest way to go about doing that is astrometry. So this is the locus of the sun getting dragged around by the solar system if you were an observer watching externally. And you can see the sun's getting dragged around a lot here. It's getting dragged around by its own diameter. Overwhelmingly, this locus, and if you could see the dates from the back, you would see that there's sort of decades. This is over decades, many decades. This is a large signal, and unfortunately, most of that's from Jupiter, and the bit that isn't from Jupiter is from Saturn. So essentially, the signal we're looking for an Earth mass is a tiny perturbation on top of this locus. So we'll come to this in a second, but it turns out that radial velocity is okay at one end of the spectrum. But if you want these Earth analogues, these FGK stars, so an Earth-like planet around a Sun-like star, if you want to find that, then you're not really in the right domain with radial velocity. And here's why. This shows you the expected signal from a habitable zone Earth. So every point here is a 1 Earth mass in the habitable zone for that star. On the left, we've got hot blue stars, and on the right, we've got dim red ones, so red dwarfs. So you can see the radial velocity signal, the RV, the signature, that's the successful method for finding these guys, kind of goes up here like this. So we've got a very, very strong signals for the habitable zone Earth mass planet around an M dwarf. And that's why these pale red dots programs exist. And that's why we know there's a habitable or a temperate planet around Proxima Cen. But you can see this signal rapidly dies, and if we want to find Earth-like objects around Sun-like stars, we need to be in this part of the diagram, where the green, red, yellow, so the green, yellow stars are. Doing that with radial velocity, we'd need 5 kilometers per second precision, and that's, in fact, falls below a noise floor imposed by the stars themselves. You could build the most stable spectrograph in the world, and you still wouldn't be able to measure this because the star itself gives you noise. On the other hand, astrometry goes the other way. The astrometric signal gets bigger for blue stars. And in the middle of this diagram here, for alpha Cen, which is kind of this solid line, you can see there are quite healthy signals. We get about 4 microarc seconds, 3, 4, 5 microarc seconds, depending on where you go, of deflection. Now, everything I've just said is a big fat lie or a cheat, because I'm comparing apples with oranges. On this side, this is the deflection on the sky from side to side. And on this side, it's the line of sight radial velocity. So it's not the same comparison. You can't put them on the same plot. But from a technological point of view, the actual intrinsic noise level from the star, the intrinsic noise level from the star for radial velocity is up here, about 1 meter per second. The intrinsic noise level from the star for astrometry is about here, at about half a microarc second. So that's why there's hope that this is the way to go. Here's our astrometric neighborhood. There's plenty of stars. This is the size of the signal that you get from astrometry, and this is how far away your star is. And you can see riding up above all the other ones with a really healthy signal, we've got alpha Cen. It's overwhelmingly the best target for this. If we absent these blue stars, which you have to wait a long time to find a planet in those orbits because it's very slow. So this is the game we have to play. If we were to play astrometry, astrometry is all about locking down your reference field. It's all about trying to measure a tiny deflection and to be certain that that deflection is coming from the intrinsic astrophysics of the system you're looking at and not some kind of warp or bend or drift in your system. It's the same as RV. It's all about trying to ensure absolute stability of your measurement frame. The way this normally works is if you just plot the fundamental noise limit. So for a 30 centimeter telescope, which is perfect and in space and has no aberrations, then you can accumulate photons, and there's a fundamental photon noise limit. The more photons you have, the better you can measure the position of something. And that plot runs like this. So this is, if you can't get there with photon noise, you may as well give up and go home. That's the fundamental limit. And it turns out for alpha Cen, you overcome the photon noise limit with a 30 centimeter telescope in only a few seconds. You don't even need an hour's worth of integration. You're way down here. You can get to the intrinsic precision you need to measure the image very, very rapidly. So the problem is you haven't anchored your reference frame. And in order to anchor your reference frame for astrometry, you've got to measure the angle. If it's wobbling on the sky, you need to measure that against something. You need another fixed point. Those fixed points are the field stars. The field stars are normally 5 arc minutes away. And the field stars at 5 arc minutes away, you're lucky if you can find something at 12th magnitude. So the field stars are out here, off the edge of the plot. And if you draw the line, you need kind of weeks or months of integration in order to anchor that reference frame. So astrometry is an expensive game. You need to build a big telescope. 30 centimeters isn't enough. You need to build a big, expensive space telescope to collect the photons, and it's not driven by your science. It's driven by the requirement to anchor the frame and get the field stars. But look, alpha Cen A is here and alpha Cen B is here. They're both bright. We can get over the photon noise in seconds. If we throw away the requirement to worry about the field stars, we only measure the separation of alpha Cen A and B. We've just bought ourselves out of the game. We no longer have to play. We don't have to worry about anchoring our field stars. We just have to measure the angular separation of alpha Cen A and B with respect to each other. So if we consider now binary star astrometry, where we've thrown away the requirement for field stars, we have a much poorer star field. These are all the binaries that are in the nearby neighborhood, and it's a lot less than the previous plot, but alpha Cen A and B are just sitting up there, obviously easy targets compared to everything else. So TOLIMAN does this. That's the first realization. Let's do narrow angle binary star astrometry. There's another thing you just bought yourself there. Firstly, you bought yourself out of the photon noise problem. But secondly, astrometry is fundamentally a game about measuring an angle of something. Is my angle varying with time? We're trying to ask the question, over 4 arc seconds, is my binary star varying in angle? Most normal astrometry is asking the question, over 5 arc minutes, is my star varying? So all of the systematic errors that accumulate in an optical system usually compound with angle. They're usually proportional to. So measuring a narrow angle astrometric signature from alpha Cen is usually a factor of 20 or 50 times easier to do than measuring a wide angle astrometric signal. So we just bought ourselves a couple of profound advantages, but we bought ourselves one big problem. The problem is, with just the binary in the field and no field stars, we have no knowledge of the state of our instrument. We don't know if our telescope just drifted. Maybe the plate scale changed. The focus drifted a little bit. The only way you can do this, if you're not using the background field stars, is you need to fly a physical object. You need to fly something that's a ruler. It's got to be a piece of material, a matter. So we need to fly a ruler. And we need to fly a very, very, very precise ruler. And I'm going to scare everyone with how hard this is. This is the image plane of TOLIMAN's sensor. I won't come to why it looks like this in a minute. But that's just an image of a star. Looks funny, but it's just an image of a star. This is the central pixel. These are the plate boundaries of the silicon. That's the atomic structure of silicon. And if we zoom in and look at the atoms themselves, the astrometric signature we're looking for on that sensor is much smaller than one atom. And we need to register that motion over 6 months. We need to watch an image move on the sensor by that much after 6 months. And then it should execute cyclic variations. So it's a very, very small signal. Suffice to say, this is the easy way to do it compared to the other methods. So how do we possibly perform image registration at this precision? So this is my daughter. I'm trying to measure the size of something. She's stepping in here to help me out with the talk. I'm forced to make this measurement in an optical system. I need to measure the size of an object using optics. Easy to do until you realize that the optics are giving you distortions that are orders of magnitude bigger than the object, than the precision you need to make the measurement. But if I could get my daughter to hold the ruler up, then the image of the ruler would be warped through the optical system in identical fashion to the image of the object you're trying to measure. So the errors and the object, the errors and the ruler are now both common mode. So if you hold the ruler out the front of your optical system, you can make a measurement which is then immune to everything, all the errors that accumulate downstream. This is the principle of a diffractive pupil. And I'm going to kind of go through it in a few little simple illustrations here. How we do this with a binary star? Well, with perfect optics, we make an image of a binary star and we can make a perfect measurement. But the world's not perfect, and any measurement we make in the image plane will be completely swamped by noise coming from our imperfect optical system. Let's instead put a diffraction grating at the front of our optics. Diffraction gratings cause side lobes. So the image will be split into a pair. Well, there'll be a straight through image, and then there'll be two side lobes due to, say, a sinusoidal grating. We're looking at a binary star, remember. So both stars will exhibit these same side lobes. But we've cooked this up. We've arranged it. We've arranged it so that the grating gives us a situation where two of these side lobes exactly coincide. We can do that by simply tuning the frequency of the grating. Now, if you think about this scenario, if you put that through a distorted optical field, you'll lose the ability to make measurements between the two stars in the binary. But if you never try to make that measurement, you instead measure something else. You simply witness the event that these two dots lie on the same pixel. It doesn't matter how badly you bend this optics, you won't be able to separate those two. They'll remain stuck together. So witnessing these two side lobes stuck together is equivalent to measuring the separation of this binary star. The separation of the binary star really does change, those two will separate apart. And it doesn't matter how badly your optics is distorted in between. Here's the way this is formulated for our mission. Here's a star which has a complicated pattern of dots now. It's a complicated diffraction pattern, surrounds it, lots of side lobes. But we're, of course, looking at a binary star. Let's just ignore all those situations. Let's just focus on those events where two of these speckles happen to lie together just by chance, and throw away the other ones just for clarity on the diagram. If we distort the optical system, then we get field distortions which kind of do this. Everything moves, but those side lobes will stay stuck together. On the other hand, the signal we're looking for, a real science signal, behaves quite differently. It'll kind of look like this. Those side lobes will move with respect to each other. So you've just built yourself a system as long as that diffractive element is stable. So you've reduced the difficulty of flying a ruler. You don't have to fly your whole telescope being an exquisitely stable ruler. You now just have to fly one object, which is a stable object. And if you can control that one object to sufficient precision, all of the other measurement errors fall away. One vision of a diffractive ruler is, or of a diffractive pupil, these diffractive dots. So you just put dots everywhere on your mirror. If you can keep them stable, they'll perform this pattern of rays, side lobes, and bandwidth smearing will streak the side lobes out into little rainbows. So you just get a diffraction pattern that looks like this one. And if you imagine you put that through a very bad telescope with gross distortions, the thing to notice is the field stars will be distorted and the rays will be distorted. So your rule is distorted and your reference is distorted. So they're both common mode distortions. The errors fall out. So as long as you perform measurements which are local, you only measure the displacement between the nearest ray and the background star local to it, then all of the optical errors have gone away. So the first vision of how to do this I came up with, you'll maybe be unsurprised given I've done aperture masking half my life. I thought we could do this with an aperture mask, so I put a plate with holes in it on the lower left here. And that generates a diffraction pattern which has got all this complexity to it. Now, one reason we can't do this, this is the original formulation of a diffractive pupil, but if you think about it a little bit, here's our star. We're actually trying to do a binary star. That other binary star would sit here somewhere. But the one thing that you don't get with this kind of diffractive ruler is you don't get any grab in the radial direction. You can't measure the separation of a binary. If you think about it, the other binary is sitting here, and there's no structure to grab onto in that direction. There's just a big streak. You can grab onto the radial component, but this diffractive ruler doesn't allow you to grab onto the azimuthal component of a change. So we need to reformulate this ruler, and that's why we came up with this mask, which gives us all of these pretty flower pattern here. And so the basic idea is that when we look at a binary star with our complicated mask, we don't measure, if we wanted to do it the old school way of doing it and accumulate errors, we would measure how many pixels there are between alpha cen A and alpha cen B, and we would count that as our astrometric signal. But that will accumulate error if your optical system has errors. If instead we count how many fringes there are between alpha cen A and alpha cen B in this pattern, then if you think about it, if the plate scale changes, if the magnification changes, you get distortion or coma, then this pattern will breathe in and out as well. So the binary will appear to move on the chip, but the ruler will move as well, and you'll get a good measurement. So this was the essential idea that underlies what we're trying to propose with this small space mission. But it was a lie, because this particular pattern looks like a nice diffractive ruler, but this is on a log scale. It's very stretched. In actual fact, if you look at it on a linear scale, the mask we had doesn't throw very much light out into the side lobes. The ruler doesn't have very many photons in it. So this was a problem And we solved this by, instead of making a physical ruler with a mask with holes in it, instead we impose phase steps on the pupil. So basically, you can take the mirror and you can carve down steps into it. So what you're to understand here by these figures is that this is a mirror and we've taken it in a milling machine and we've just carved down half a wave wherever you see black. So wherever you see black, the light will be in antiphase with white. So it acts a little bit unsurprisingly. These are kind of log harmonic spirals. And these act to throw the starlight out of the core and into this pattern of fringes. And for people who are into coronagraphs, they'll recognize this as not very dissimilar to a phase vortex coronagraph, which is why it's got a hole in the middle. So basically it nulls the core. We actually don't need to null the core. So we unbalanced the coronagraph a little bit. We added a little bit more pi than 0. And it turns out you can effectively fill in a point spread function like this. So one of the things we need to do is to be able to fabricate a mirror that is able to really mess up the point spread function in an utterly comprehensive way like this. And then if you went to look at the binary star alpha Centauri and you rolled your spacecraft, you would kind of see these two patterns interlacing with each other. So that's the signal we're looking for. We're trying to register those two images on the right. So we've just accumulated a bunch more advantages for our system. The diffractive pupil removes the errors from the optics, and it spreads the starlight over lots of pixels. Lots of people who do photometry, they want to spread their light. They defocus their telescope. This does the same thing. It gives you many pixels rather than a few pixels. So you don't care so much about flat field errors. And then we found another flaw. It's all very well to keep a plate stable in a telescope, and we think we can do that. We can keep our ruler stable. But this diffraction pattern is made of two things. The first thing it's made of is the first thing this depends on is the physical stability of the plate that's doing the diffraction. And the second thing it depends on, of course, is the wavelength of the light. The ruler is depending on the wavelength of the light coming from the star, because it's a ruler made out of starlight. And that's a problem, because stars aren't lasers, and stars don't have a stable wavelength reference. So we found this flaw in our system at this point, that we couldn't get adequate stability of the exact effective wavelength that the star was giving us. Because all the star's got to do is drift by several tens of degrees Kelvin, and the center wavelength will shift by a minuscule amount, and then the fringes will breathe in and out, and you just think your binary moved. So we had to come up with a whole separate system, and this is where the going gets kind of much more Fourier and much more complicated. So warning in advance, sort of some shifty Fourier stuff coming up. We needed to build a spectrometer. So here's our funny pattern in the middle that we register the astrometry with. And then we put a spectrometer out here. And the spectrometer does two things. You can measure the effective temperature of the star all the time. So you can know if it's changing temperature. The second thing it has is out here there'll be little spectral lines. There'll be calcium and carbon, whatever you find in the atmosphere of a star. Those form little atomic clocks. And the atomic clock gives you an absolute reference. So there's an absolute encoding of the plate scale, going all the way back to, it's basically like a laser. It's giving you a wavelength reference. Calcium, carbon, whatever they are, they give you a wavelength reference. So it gives us two ways to stabilize the plate scale. Firstly, the effective temperature. Secondly, we look for the stellar lines, and we use those as clocks. And it turns out that we can do that. We can get data that has these little spectra in it, and we can recover the spectrum of the star and find the plate scale. Now, we have a problem, and that's we've got competing design conflict here. On the one hand, we need this diffractive ruler to make the worst possible point spread function for a telescope. We need that to be ultimately as messy as it can be. It needs to have lots of edges so we can grab it. It needs to spread the light over many pixels. On the other hand, we need to make a spectrometer, we need to make a spectrometer out of these side lobes. So this is the world's worst grating function. This is a big, messy slit with a big, wide aperture. We have a very poor spectrometer because we've just convolved it with this terrible point spread function. So there's a competing design requirement. Out here, we want the best possible point spread function, and in here, we want the worst possible point spread function. How do we do that simultaneously with the same optical system? So it turns out that Mr. Fourier is kind of a magician, and you can get both of these things to happen at the same time. What you have to do is to take the primary pattern, which has the phase steps of 0 and pi in it, and every time your grating runs along and it crosses one of these boundaries from 0 to pi, you flip your grating upside down. And then you go along and then you flip your grating back the other way. And you get this magical property. It's completely fell off our chairs when we figured this out. You can have the point spread function in the core being this horrendous mess, and then the point spread function out in the side lobes is essentially a diffraction limited area disk. It just doesn't see the bad pupil at all. So we've got our cake and we've eaten it too, which seems impossible. So this is kind of the diffractive, we call this a doubly diffractive pupil now. And in fact, we kind of went to town. We put these everywhere. We put one on the secondary mirror as well, maybe. So we've got a very, very stable telescope, and our ruler, the ruler we're flying in space, is an extremely stable piece of 0-dur or something with this funny pattern. It's got this combined set of gratings and carved steps on it. So we can get this kind of, a data field might look a little bit like this, where this is our primary star, this is a point spread function, this is our primary star, and these are the spectral side lobes. So we extract our spectral information out here, and we get our astrometric information in the middle, and everything cross-calibrates. It's all very well. So now we've got, I'm just accumulating all these gains that we're trying to implement with this architecture in order to get to that crazy, less than an atom reflex motion that we need to find at the end of the day. We've got a doubly diffractive pupil. It delivers monitoring. And we believe that for a small, cheap telescope, rather than a big 1 meter class telescope that you need for the field stars, we might be able to get to this kind of signature science, this kind of top shelf detection of a planet around Alpha Centauri. Here's what our actual data field would look like in the end. We have these side lobes out in the corners, and we've got this funky diffraction pattern in the middle. So it's shown a little bit enlarged here. It would actually be this size. We think we can handle a lot of the hardware issues here, the mission. It doesn't look like any of this is out of spec. We can get enough data down, we hope, from this small telescope. So as a Pathfinder, we're launching in May next year a thing called TinyTOL, which is a little bit more than, it's a 1-inch optic with a lens. So it's not going to do astrometry, but basically it's a CubeSat. The blue part, it's even a small part of a CubeSat. It's just a Raspberry Pi camera, so something a hobbyist could really put together in some sense. But for the TinyTOL, we've built one of these pupils. This is what the Pleiades would look like viewed with the TinyTOL instrument. You've seen these tri-spirals, these logarithmic tri-spiral, which was the original, this logarithmic tri-spiral, which was our original design. And it gives us, so what we're trying to do here is make the best possible pupil. It gives us a fairly good spread of the starlight, but there's still some regions where it's a lot brighter than others. Really what you want, I describe it as a bed of nails. You want all of these speckles to have a uniform top. You want them all to be super bright and super sharp, but you don't want there to be any that are a lot brighter than the other ones. It's about suppressing the dynamic range. And then outside a certain radius, you want all of the energy to go away. So you want a sort of a tabletop of sharp spikes is the optimal answer we're looking for. So we fed this pattern into a Gertzberg-Saxton phase recovery, and we said, okay, this is what it gives us, but what we really want is a bed of nails, and we just let the computer iterate, and it turned this into this. And you can see that this is now a lot more uniform, and if I put it on a log stretch, you would see there's actually a lot of energy out in the wings, which has kind of gone away here. So with the computer, we're able to optimize this diffractive pupil property. And we had one made. This is a $20,000 piece of glass that's about this big. It was made by a fancy company in America. And so there's this tiny little pupil. I'm looking at it here through my sunglasses because it's the only polarizer I had at the time. But you can see it's got this pattern embedded on it. And it's also got those other, here's a blow up. You can see there's the fringes going in two different directions to make those side lobes. And then you can see the primary pattern. So this is this little waist here, I think it's that bit there, I don't know. Anyway, so we made one of these. We put it through an optical rig. And it does exactly what Mr. Fourier told us it would. It was amazing. Here's a laser illuminating it, so you can see you get this really, really messy point spread function in the core. And you get basically diffraction limited area disks out here in the side lobes. And when you put it with a broadband source, in fact, this is a laser diode, you can see that these streak out into little bandwidth smeared rainbows. And we've got this pupil in a number of test beds around the world. One of them is at NASA Ames. And so this is kind of what a binary star would look like if you were looking at it through this system. And the name of the game now is about trying to fingerprint these two things. You want to register exactly where those two stars are, and you use the whole pattern. You don't just use the cores. And I'm sort of nearly approaching the end here. This is kind of all just mission stuff now. So we just talked about TinyTOL. The next thing is called TOLIBOY. Don't ask me how it got that name. I'm not too happy with it. This is a 10 centimeter kind of Pathfinder, and we're trying to trying to understand these data forms. So there's lots of participation from various places in Italy in this. But we've got partners all over the world. The Japanese are keen, the German Space Agency, OHB is going to be our spacecraft supplier. We're just trying to get all our ducks in a row so that we've got some money already promised, but this is not enough. So we're trying to get more money out of the Australian government to complete. And in fact, the OHB are also contributing a whole bunch of in-kind support. So it's very exciting. We hope to launch this in about, I don't know if I've got the right date on this slide, it's about 2022 now. Yeah, I say 2021. 2022, 3-year mission. And then down the track, maybe we'll go for that 30 centimeter one that I first put up, or a 50 centimeter telescope. And still further down the track, there might even be a larger mission beyond that. I think, yeah, we already sort of talked about this. One point I want to make before I close, you don't get everything you wanted to get out of this. You're only measuring a very simple quantity. It's just the separation between these stars. So if there's a planet orbiting in the plane, that will tug the binary this way and you'll witness a signal. But if there's a planet orbiting in a polar direction, then the binary is doing this and you won't see that binary. So we have a kind of a Sinai ambiguity. Planets can still run and hide. Except that if there's a planet in a polar orbit, it won't be dynamically stable in this system anyway. So planets in polar orbits are forbidden by the binary itself. So there may be some small ambiguity, but mostly with a little bit of dynamical analysis, you can probably figure out what the planet is. Well, another thing you don't get, of course, if you see a signal, you don't know which star it came from. You don't know if the planet was around this star or this star. So it's a way to detect something, but not necessarily a way to get all of the information you like. And of course, maybe there'll be a major mission if this works, possibly further down the track. So here's the artist's conception you've probably seen. This is an idea of what life might look like on the Proxima Centauri planet. And you can see here in the sunset, there's Alpha Centauri A and B, as they would appear from Proxima. They're even actually quite faint stars in Proxima's night sky. Proxima is so far away. But I think the exciting thing is to try and find something actually a solar analog, an Earth analog around a solar analog. So for that, you've got to go looking over here. I have my doubts whether Proxima itself Proximus NB will host life. Okay, so I think I'm going to stop there and thank everybody for their attention. Are you magical? Are you kind of like... you can...
Today. So is there any questions for Peter?
Well, all of the question is what we cannot get from Gaia, all of this.
This, to get this signal...
We cannot get. So how is complementary?
With Gaia, you said.
So Gaia has an end of mission astrometric precision of about 7-10 milliarcseconds, microarc seconds. We need microarc seconds.
Microseconds, but down. And that from
10 microarc seconds, right?
Below that from bright stars.
Sorry.
Below that from bright stars.
Well, stars of zeroth.
Few microarc seconds.
Zeroth? Are you going to say you?
No micros. Few microseconds. No, it's just a.
Okay. I mean, well, my vision of it is.
Unit for specific research, but I want to understand what it's
Gaia, the binary,
I haven't met anybody who claims that Gaia will work.
and also maybe
I haven't met anybody who claims Gaia can work on stars as heavily saturated as Alpha Centauri. So maybe. I've just been talking to Alberto Krohn-Martens, who's one of the main data analysts on Gaia, and he wasn't confident that you would get much below 7, even on stars for which it's most favorable. But for Alpha Centauri, it's heavily saturated. It's a 0th magnitude star. It's very, very bright. I think well, maybe, I don't know. There may be, you need to pull information way out in the halo to do that, because the core is saturated and it's bloomed and it bleeds the whole chip out. So it's very, very difficult. So that's one point to make. We need to get about half a microarc second precision with this. So it's a completely different thing. It's staring at one star. Gaia does 1 billion stars, and it's really stars. I mean, hands off to it. It's stunning for what it's doing. You know, I can stare at one star and maybe get down to a microarc second, half a microarc second. And Gaia's doing 10 microarc seconds for everything in the sky. It's just amazing value for money. But having said that, I don't know if Gaia could get down to these levels of precision. Yep.
I suppose you must have a very stable telescope.
Yeah, you do the best you can. Yeah. Yeah, I mean, it's all very well to say we don't care if the telescope bends, but of course, you want your telescope absolutely rock stable. And then so OHB are our primary suppliers, and they're claiming they can get, well, firstly, you keep it as stable as you can. So I think the spec is about half a degree, and the plate itself has to be even better. You need to monitor it. So if you have a thermal model, you can breathe the model and undo the effect of the breathing on the data, if you can learn that. So there's one level at which you need it stable, and then there's another level at which you need to know what's going on. And even if you don't correct it, you just, even if you don't mechanically recover. So it's got its own onboard, we run it hot so that we keep heaters going so that it stays above thermal. But yeah, so you do your best, and then you measure the rest, and then you have a big model to undo whatever's left over. Yeah, it's a hard game.
Is there also some passive control of for instance, of the expansion? If you combine material with different expansion indices, you may have further reduce the relative motion of the optics. And so on.
Yeah, the idea is to try and make everything out of a single material. So try and manufacture the entire telescope, for example, out of zero-door or ULE glass. And then you have no differential. That's what they did with Gaia, right? I don't think we've got the budget to melt everything into a block the way Gaia did, but yeah, that's the plan.
This kind of design is used also for continuous objects or only for
instance, an asteroid with a plate shape. Solar planet system. Planetary system objects.
That's a good question. My first instinct is not instantly. It's not instantly as relevant. You mean for astrometry of, say, binary asteroids, or?
Because you need the binary asteroids to measure.
Well, binary asteroid is the same situation as here, but
But bright enough.
asteroid.
It's not intended as an imaging modality. It's intended simply to do this astrometric measurement. If you had I mean, my first instinct would be that if it was spatially resolved, then it would be difficult because the pattern, that sharp pattern, would start to blur with the point spread function. You convolve that sharp pattern with whatever the real image of your asteroid is, and you'd lose the power in those fringes. The power in those fringes are what gives you the ability to grab onto that fingerprint. There's a quantity we optimize called the gradient energy of the image, which is how many photons are landing on slopes. And the more photons land on sharp edges or slopes, the easier it is to register an image. This is why RV is hard, because when you look at a spectrum of a star, there's only a small number of photons that land where the lines have sharp edges. Most of the photons aren't helping you with RV. Only those photons which land right on one side or the other of the line, the calcium line, the carbon line, the helium, or whatever the lines are. So if you blur the pattern, you're entering a domain where the measurement will degrade. Sorry.
Okay, so thanks again.
Thank you.
You will remain in laboratory or in our offices for the afternoon.
Yeah, and thanks for taking a talk out of the sequence. I know that's kind of, your schedule's all.
Okay, thanks a lot.
Thank you.